Welcome to the Deep Dive. If your mission is to gain knowledge quickly, thoroughly, and with enough context to actually make it stick, you are definitely in the right place. Today we're setting the Wayback Machine to 2017, but we are looking forward, all the way to 2030.
We are.
We're diving deep into a really foundational piece of analysis. The paper titled Assessment of Midterm Growth Assumptions and Learning Rates for Comparative Studies of CSP and Hybrid PV Battery Power Plants.
This study, which was led by Christian Breyer and his team, set out to do something vital. They wanted to establish a robust, transparent foundation of capital expenditure.
Our CapEx.
Right, CapEx projections for the major solar technologies. So concentrating solar power, photovoltaics, and Li-ion batteries, looking ahead to 2030. And they did this using the very well-established experience curve approach.
And even though the paper's from 2017, its methodology is, it's absolutely timeless. It gives us the context we need to understand the fundamental drivers of cost reduction in renewables.
Exactly, especially when you're analyzing systems that need to provide flexible, dispatchable power.
Which is the core question here, right?
It is. The whole study is built around this question of flexibility. Concentrating solar power, or CSP, has this inherent flexibility because you can easily pair it with thermal energy storage.
That's GES, yeah.
But PV, which has obviously dominated the market, needs this whole ecosystem of other parts, battery storage, plus a backup like a gas turbine to get that same kind of reliable service.
So this study makes that definitive apples-to-apples cost comparison.
For two fundamentally different, yet, technically equivalent systems.
Okay, so let's start with the engine room of this whole thing.
Yeah.
The methodology. How exactly does the experience curve approach turn historical data into a 2030 price tag?
Well, it really simplifies what can be a chaotic market into just three clear variables. It projects future costs based on, 1, historic cumulative production.
Okay.
2, our assumptions about future market growth. And 3, the technology's own specific learning rate. It's basically modeling how an industry gets more efficient as it gets bigger.
That brings us right to the most crucial term in this whole discussion, the learning rate. For anyone listening, can you just define that for us? Why is it so powerful?
The learning rate is, it's the measure of progress. It's the percentage decrease in the capital expenditure every single time the global historic cumulative capacity of that technology doubles.
So a higher learning rate means rapid scaling is rewarded with these really rapid price drops.
Exactly.
And the starting line for this race using 2015 data was, well, it wasn't even a fair race.
Not at all. PV had a cumulative installed capacity of 230 gigawatts.
230.
And CSP had only reached 5.0 gigawatts.
Wow, just 5. That disparity in scale is really the ghost in the machine for the rest of the projections, isn't it?
It is, and that initial gap directly influenced the learning rates the authors chose from their literature survey. For CSP, the rate was pretty conservative, typically between 10 to 12%.
So every time CSP capacity doubled, the cost would drop about 10 to 12%.
Right. But for photovoltaics, the learning rate was dramatically steeper. Historically, PV modules had rates around 20 to 21.5%.
And that's already high.
It is. But crucially, the authors noted that in the years right before 2017, PV modules were showing a learning rate of over 30%.
30%? That's incredible.
They did model a slight reduction, but that staggering pace just shows you how mature and globally deployed PV already was. Li-ion batteries, which are key for the hybrid PV setup, were also modeled with a strong learning rate, around 20%.
Okay, so this is where the numbers start telling a real market story about risk. We have these strong learning rates for PV and batteries, but the uncertainty in market growth predictions for CSP, it was just staggering in this study.
It is probably the single most dramatic finding about the CSP market at that time. To quantify it, the authors looked at the huge range of different studies predicting total installed capacity for 2030.
And they calculated an uncertainty ratio.
Exactly. The maximum projected capacity divided by the minimum.
So what were those ratios? Because I know the numbers are just wild.
For PV, the uncertainty ratio was a factor of 5.1x.
Okay, 5 times. Significant, but you can sort of wrap your head around that.
Right. It's within reason for a growing technology.
Yeah.
But then you look at concentrating solar power, and the uncertainty factor was a monumental 66.8x.
66 times? How is that even possible? That means some serious established analyses were projecting fundamentally opposite futures for this technology.
It all connects back to market maturity, or really the lack of it for CSP.
I see.
The small deviation for PV reflects its huge installed base. It was predictable. CSP, though, was still, struggling to find a stable growth path back in 2017. A 9 GW low-end projection meant the market just dies.
And then the 635 GW high-end.
That reflected a hyper-optimistic scenario where global policymakers suddenly demanded its dispatchable power capability. The market just hadn't decided on CSP's future yet.
It's a perfect example of how market uncertainty can just kill momentum, no matter what the tech can do.
Okay, let's pivot from that enormous uncertainty to the concrete base case projection. What do the 2030 CapEx numbers actually look like? So based on that base case scenario, the capital costs per kilowatt were projected to look very different by 2030. If we look at the average figures.
Yeah, let's hear them.
CSP tower was projected at 2,939 euros kilowatt.
Okay.
CSP trough, a bit higher, at 3,425 euro-watt. The standalone PV plant was, as you expect, dramatically lower at 693 euro copper.
Of course. And the batteries.
The battery plant, measured by energy capacity, was projected to be just 173 euro-watt-hours.
Hidden inside those CSP numbers is a really big story, a changing of the guard almost.
You mean tower versus trough?
Exactly.
Yeah.
The analysis suggests that within the CST market, the tower design is set to undercut the traditional trough technology on cost.
Right.
That's a huge internal market shift.
It is. This projected cost reversal tower becoming cheaper than trough is a massive indicator. It suggests that capital would naturally start flowing away from the older trough design toward the newer tower technology.
Which would then drive its own specific learning rate even higher. Now, let's get into the component analysis, because this is where the nuance is, especially for flexibility costs. When we talk about a CSP plant, it's not just one number.
Absolutely not. The overall plant cost is kind of meaningless if you start changing factors like the solar multiple or the storage hours.
Which you have to do to size a flexible plant correctly.
You have to. So the study had to break down the component costs because all those different parts have their own cost decline trajectories. The solar field, for example, had a strong learning rate of 10%.
10%.
The thermal energy storage was a decent 8%. But the conventional power block component, the turbine, the steam engine, it only had a 2% learning rate.
2%. That's almost stagnant compared to the 20 or 30% drops we see in PV.
It is.
So no matter how cheap the mirrors or the storage tanks get, the cost of that steam engine is just sticking around. That puts a real ceiling on the total cost reduction for CSP.
It's the Achilles heel of any thermal power generation system, really. If you want to understand the true levelized cost of electricity, the LCOE, you have to get these component constraints. And this study provided that transparency.
Okay, here's where it gets really interesting for me. The true comparison test. The study designed this scenario to compare the cost of a single standalone CSP plant against a technically equivalent hybrid PV system.
One that could provide the exact same reliable, dispatchable power profile.
So they set the benchmark. A 100 milliW CSP tower plant. It had a high solar multiple of 2.4 and a lot of storage, 10 hours of thermal energy storage.
And for that system, the projected 2030 CapEx range was between 2,826 and 3,052 kilowatt.
Okay. So now for the PV side, what did they have to build to match that exact same output?
Well, the hybrid PV system had to be complex. I mean, it was almost a Frankenstein's monster of components. It needed a massive 282 milliwatt of PV capacity.
Almost 3 times the rated output.
Yes. Alongside an enormous 448 milliwatt of battery capacity and a 100 milliwatt gas turbine for backup.
Just to make sure it's reliable when the sun's not out and the battery's empty.
Correct.
That is a staggering amount of hardware, just to mimic what the CSP plant does with mirrors and molten salt.
Yeah.
So what was the final projected cost for that heavily engineered hybrid system?
Once they factored in all of it, the PV, the massive battery, and the 475 euro for the gas turbine, the total CapEx for that hybrid PV battery TT plant in 2030 landed between 2,917 and 3,505 eurowatts.
Wow. So what does this all mean? We have 2 completely different ways to get reliable solar power. A single integrated system versus a complex, redundant one. And their CapEx projections for 2030 put them in a dead heat.
That's it. They emerged as technically equivalent solutions with really comparable CapEx values right next to each other.
Which means the market competition for dispatchable solar was poised to become incredibly fierce.
And this wasn't just some theoretical model. The authors noted that their findings, this idea of cost parity, it actually matched the internal market insights and expectations of a potentially major solar investor, Saudi Aramco.
On all 3 technologies.
On all 3. That kind of validation, it just speaks volumes about the rigor of this 2017 projection.
That is a powerful conclusion for a paper written years ago. Let's try and summarize the key takeaways for you, the listener.
Go for it.
First, cost decline, driven by these aggressive learning rates, meant that by 2030, a single CSP tower and a complex hybrid PV system were projected to be equally competitive on capital cost.
And second, that the massive market uncertainty back in 2017, that incredible 66.8x range, lay squarely with CSP's growth, not PV's.
Right.
Ultimately, this study provided the transparent CapEx assumptions that you need for any follow-up LCOE comparisons, which, is what really determines profitability. It showed that both pathways were viable.
And it even suggested that combining them, like in hybrid CSP PV, could be the ideal setup.
For grid stability, yeah.
Which brings us to a final provocative thought for you to consider. Remember that drastic 66.8x uncertainty range for CSP growth.
Hard to forget.
If the market had realized that high-growth scenario, that 635 GKD of deployment, how might that rapid scaling have accelerated the learning rates for CSP components, especially that critical lagging power block?
Right, the 2% piece.
Could a massive investment surge in CSP have just drastically altered its competitiveness against the already established, rapidly falling costs of Li-ion batteries? It's a compelling question about missed opportunities and, really, market momentum.
It is.
And that brings us to the end of our deep dive into the research from Christian Breyer and colleagues, specifically the paper Assessment of Midterm Growth Assumptions and Learning Rates for Comparative Studies of CSP and Hybrid PV Battery Power Plants.
Thank you for joining us.
We'll see you next time.